Alrighty. We've been having a great run with the sort of Q&As over the last few weeks. And as I think a good near half, at least, of the internship is focusing on machine learning to some extent or the other. So we just had to have opportunity for everyone involved in machine learning to come through and ask their burning questions. In particular, how to get the most out of their allocation and why we might prefer certain workflows on systems like Topaz. And joining us today are Christian and Pascal, who are both supercomputing applications specialists. Is that the?
Yeah, that's right. That's very complicated title, but it's good. That's one.
Yep. Yeah. So their day-to-day work is kind of advising researchers and optimizing software and designing the sort of workflow that everyone that all of you are interacting with. So I guess to begin with, Christian and Pascal, would you like to just give a little intro to yourselves and your background?
Yeah, definitely. I'll start.
It's
That's not me.
No, that's. I do apologize. I do have Etienne with me, so my young son, who's 2, is going to be in the background chatting a little bit.
No worries. Well, my name is Christian. I've studied computer science and now working as a supercomputing application specialist at Pawsey. My main focus, as Edric said, is helping researchers running big simulations and big computation on the supercomputer. It's not as easy as using a normal computer, as you may be aware. So they need a little help to configure and to prepare their programs such that they use in an optimal way the resources they have access to. In particular, I have expertise in GPU programming, which are used nowadays also especially for machine learning tasks. And so that's why I'm here as well. Over to you, Pascal.
Yeah, so as Edric mentioned, I'm a computing application specialist. My background was computational astrophysics. So I did lots of simulations of essentially fluids at high Reynolds numbers in a generalist relativistic background, trying to model large-scale universes and explore various problems in galaxy formation and cosmology. As part of that, I learned lots of MPI programming and programming threads. Also, as a part of that, I wrote a lot of algorithms about clustering and about how to extract signals out of data, right? So that involved not just mucking around with clustering algorithms, but also mucking around with networks, usually GAN, generative adversarial networks. And my GPU programming started way back when, but I didn't do huge amounts till recently. So once I joined Pawsey, I did a lot more GPU programming in earnest. And hopefully I can help you with any questions you might have. Cheers.
Thanks, Christian and Pascal. So I encourage everyone to just come forward with any questions you might have. Said it's an informal session, so yeah, feel free to take this where you'd like to go. Anyone have something they'd like to start with?
I'll get the ball rolling by asking everybody, what are they trying to do machine learning wise or data analysis wise in general?
Yeah, let's so I'll just pick folks as they appear right to left of my screen. So Jamie, give us a quick rundown of your project.
I'm using the chat because I'm not supposed to speak in the silent section.
It's all good. So while you type that out, Dina.
Yep. So what I'm trying to do is mostly computer vision focused. So I'm trying to build a machine learning model where I can feed the medical images to the model. And then on the other side, I can get the predictions about like the survival rate of the patients.
That's very interesting. What type of images? What type of things are you working on?
So my main database is a collection of whole slide images, which are like these large images in .svs format. So I have like 400 or so of these images, and then because they're so large, I need to break them down into smaller patches and then build my model, then just feed them into the model as training and testing data sets.
Go ahead, Chris.
Go ahead. No, I just wanted to ask, are you using a pre-trained model and then you are using transfer learning, or are you training a model from scratch?
Oh, I'm training my model from scratch. So we have this paper that has done a similar job before. They have already made a model and they've provided the technical details. So I'm just trying to basically reproduce their code. And that's just basically they have like a multi-architectural model. So, and they train it from scratch.
Right. So I'm curious, you said you have to break up your image. I mean, if you're deconstructing an image, you're already slicing up possibly information across boundaries of what you're doing. So what exactly do you mean by your image is too large? Like it can't fit into the GPU memory?
Yes, exactly. The images, so it has got like different layers and different like zoom layers that you can use. And the native basically magnification is just too large to fit onto the GPU and just fit it into the model. That's why I need to like break it up into like smaller PNG files.
Right, but I mean, okay, so I understand essentially blurring an image, but slicing an image, maybe I'm missing something, because if you're slicing an image, you could be slicing regions of interest, right? So, I mean, it's very true that if you capture an image, you might capture a portion of a tumor, let's say. So you might not capture all of the tumor, but do you think they would try to reset and always capture the region of interest? So I'm assuming the image should be focused on the region of interest.
Yeah. Sorry, go ahead.
No. So I'm just trying to, because if it's simple imaging, as it were, but the image files are large, then the GPUs on Cytonix will be very large in terms of memory. So are the files larger than 64 gigs?
I'm not quite sure about the size, but so the pre-processing, in addition to like putting into slices, so the image already has background and a tumor. So we sort of need to basically get rid of the background information as well, because we don't need them to feed into the model. So part of that patching process also involves identifying those background regions and then getting rid of them as well.
Well, that's interesting. I would have never thought, I would probably have said like, that probably is not true. But I haven't read the paper, right? Because background information, if you don't know the ground truth and you're trying to determine the ground truth, the background might be very useful for judging survival rates, how the tumor is interacting with the background. I'm just surprised that I thought that that's an okay path. But anyway, that's just me.
Yeah, that's how they did it in the paper. So I'm just trying to reproduce. Yeah.
Okay, interesting. But it's a good thing to keep in mind, right? Because if it is background, I mean, especially with something that's meant to interact like long range interaction, I imagine the background is actually quite important, because how a tumor grows is probably dependent on itself and the environment.
Yeah.
So I can't imagine that you'd pick up the information necessary to determine something unless you actually also sample the environment it lives in. It's not like a stop sign. Where people are just trying to do automated. Stop sign doesn't have to interact with its environment, you just capture it. But in this case, you're looking at something as a function of time and being able to predict how it behaves in an environment. So I'm very surprised that they can do this. But that's cool.
But that's an interesting point. I'm gonna bring that up with my supervisor about background. Thank you.
Thanks, Dina. Helen.
Hi. My master's is in machine learning and data science. So I'm sort of building on things I've done in that. My project is about, it's kind of morphed a little bit from just being sort of a vague crypto-based thing to looking at social engineering detection in maybe the Ethereum blockchain network versus the Bitcoin network. So currently we've identified a couple of data sets. There's two approaches. One is there's been quite a lot of work done on looking at the machine, mainly on classification, looking at the detection of social engineering scams within a network itself. But what we're sort of interested in is taking an offline sort of data set of hacked or illicit scammed email addresses and see if we can map that to, say, the Ethereum blockchain and detect if there's any correlation between what's happening offline and online. So we're looking to use graphs with the Neo4j product to really see if the features available through the offline data set are comparable to what you're seeing on Ethereum. So it's really kind of, it's morphed a little bit from what I thought it was going to be, but it's really sort of focusing on, can you identify specific things about social engineering attacks, or the fact that you have a different profile when you're just looking at the transactions on the blockchain, as opposed to when you've got socially engineered hacks on websites and then they get transferred to the blockchain itself. So it's trying to see if there's a way of detecting differences in those kind of profiles, I guess. So it's a little bit still, we haven't completely bedded down how we're going to use the actual which model we're going to use at the moment, but it's not going to be image based. It's CSV based. Trying to look at, say, particular activities within an account and you know, what sort of lengths of time, for example, transactions take, or clusterings of transactions around a particular node, that sort of thing. So yeah, it's still a little bit trying to find the actual path through, but it's definitely going to be a classification problem using probably something like XGBoost or something like that, which is, well, you know, will take quite a lot of computational power, but the details are still yet to be decided. So yeah, that's where I am at the moment. But certainly with the graph side, that'll take quite a bit of process power as well. So it's almost like a two-stage thing where we look at the features via the graph embeddings and then take that to the machine learning bit, where we decide based on those profiles, you know, which model might be a better fit for this particular type of work.
Right. That seems pretty cool. I can ask, so that you haven't done no one's kind of looked at the graph yet, right? For features in the offline data you said that you're going to focus on, right?
There is quite a bit of work using graph technology as a way to look at the actual, it's more on the actual blockchain that it's been done rather than looking at the offline side and then comparing. So I think that's where the novelty of it is.
Right. So I guess the expectation is you'd expect activity to be a feature, but you don't necessarily have an indication of the features yet because no one's kind of done this sort of exploration yet.
Yeah, I mean, I've got the feature importance from other models that have been generated from that offline database. But when you map it to the graph, I'm expecting it to sort of maybe bring out something different.
A bit more complicated stuff, yeah.
Yeah.
That's
so
cool.
It's just whether or not, I mean, those two things obviously don't marry up in, you know, the model is a separate thing to the graph processing, but the graph side of it will give us what we need for the model, sort of thing.
Yeah.
So it's going to be a model comparison, deep learning. Probably it'll be an ANN or something like that. But you know, hopefully I can use quite a few layers, whereas when I've done it just on my local machine, it's been very limited in terms of processing capability.
Yeah.
So yeah, I'm hoping I can sort of, I'll be able to get maybe 2 or 3 extra layers from what I've done before.
Thanks.
Thanks, Helen. Next, we've got Jordan.
Hi, everyone. I hope you can hear me all right. So my project is predicting surf conditions, and that will take in a bunch of frames from different buoys. And basically what we're doing is action prediction, where based on those past frames of wave spectral energy, predict what the future wave spectral energy will be at the location we're trying to predict. Yeah, that's pretty much it. And I only just built a really basic model, and my supervisor literally said at 9:30 today, see if you can get it running on Pawsey today. And I looked at it and I saw this meeting was today. So that's very useful. Yeah, that's pretty much it.
Cool. What type of model are you using?
Pardon?
What type of model are you using?
Yeah, 2+1D. So it's like a 3D convolution, but it separates the convolution into a 2D spatial convolution and a 1D temporal convolution.
So seems like, well, there is a bit part of computer vision at first, but then you have the temporal modeling that you need to do. And that one, sorry, you said that it's already incorporated in the model, because I was thinking about long short-term memory networks.
Yeah. My supervisor said 2+1D was better, but he did give me papers on long short-term.
Okay.
I think he has tried it before, but the 2+1D works better.
Okay, interesting. I'm not familiar with that one, so.
Yeah, I would never have heard of it if my supervisor didn't tell me about it. I don't know how obscure it is. But
for the Pawsey part, I guess, well, you have Topaz available now as an intern. Hopefully next year, if the project goes further, then you will have an allocation on, depending if you applied as well, you can have an allocation on the GPU partition of Cetonics, but that won't be until probably February next year.
Oh, so we can't use GPUs at the moment.
Oh, you can use it. You have the NVIDIA ones on Topaz, the V100s.
Okay. Oh, so on Topaz I can't use Cetonics, or?
Oh, Cetonics doesn't have GPU at the moment.
They're physically inside a cabinet, but they are not powered up, and you cannot do anything to them.
Okay, yeah. I've been under the wrong. I think I need somebody to tell my supervisor that. So you use Topaz at the moment? Is that?
Yeah.
Yeah, cool. Thank you.
Also for everybody here, right? So if you're using Python and Pythonic workflows, etc., then you're probably fine because all the stuff is there. You can just kind of launch something that would know about CUDA. You can grab a container as well if you're trying something, but there are tons of containers in there. For Cetonics, I mean, when the GPUs will be available, that's still an open question exactly the when, but also we have not, I don't think anybody's actually run a container of the AMD versions of, let's say, TensorFlow, the containers, to see how well they perform and how, if there are any bottlenecks we have to consider running on AMD GPUs. It should be fine. They've put a lot of effort in, but Christian, correct me if I'm wrong. I don't think anybody that we know of has tested in earnest an AMD deep learning container on an AMD GPU.
So for what I've seen so far, they seem to work as like the ones running on the NVIDIA hardware. I haven't tested that thoroughly, but for basic models, they seem to work fine.
Okay.
All right, thank you.
Thanks, Jordan. And last we have Abraham.
Okay. Hi, can you hear me?
Yep.
Okay. Yeah, well, my model is about corrosion and specifically about an alloy called duplicate stainless steel. It's a specific alloy for producing oil and gas, which can be a little bit, can optimize the cost for producing hydrocarbons. However, there is a problem, a corrosion phenomenon called stress corrosion cracking, and this material can be very susceptible to this corrosion phenomenon. So I'm constructing a model to predict the occurrence of stress corrosion cracking, but I'm using another approach apart from machine learning called Bayesian networks. Now, my model with Bayesian network is already completed. I just need to tune certain aspects. But for this internship, I'm training another model using the stream gradient boosting, which is the XGBoost model, in order to compare them, because the connections in my network can be a little bit more, well, I have no experimental evidence. I have only certain data coming from different sources of information, standards, experiments, corrosion reports, something like that. But running experiments to validate the model or at least calibrate the model can be very difficult because it implies utilization of hydrogen sulfide, high temperatures, and for a PhD, or at least for a PhD student, for safety reasons, it's not feasible. But using another modeling approach can be, well, we can compare them, we can analyze the connections, interpret the model, and then I'll compare the accuracy of both models, and actually not only choosing, but actually support each model, just to know how can we improve the accuracy of my Bayesian network, and more or less just, well, that's the objective of this internship. At the moment, I just complete my script for training the XGBoost model. It's a problem of classification, of course, and actually as well, I work in, for hyper tuning the model, and as well for cross validating the model using nested cross validation. So I'm just working in the process of creating or building a container and working with photonics as soon as possible.
Thanks, Abraham.
That sounds a good project, and also using Bayesian networks when they work, if they work, then it's good. You don't need to resort to huge models if simpler ones work.
Sorry?
No, I just said it's if by the Bayesian networks work as a model, then you did a good choice, and you don't need to go with a more complex model if they provide just minimal gains.
Yeah, actually, the point is just compare both approaches, because the problem is that given that we cannot validate the model experimentally, we need to compare them with another that can be easily interpretable, such as an ensemble model. So that's the good thing, because after training the model, I can use this kind of approaches for interpret the model, which is the line or the Shapley decomposition, and they can show you more or less the connections and interaction between the variables, between the factors, leading to stress corrosion cracking. So we can improve the connections to the Bayesian network. And that's it. Using both approaches can be very useful, because the Bayesian network can be used for experimental models, experimental validations, interpretation of the entire environment, while the XGBoost can be used for a single prediction. If you have to choose an alloy and you choose the factors or something like that, that can immediately give you a single data point, a single prediction, and that's what we want. So we can go using both in different aspects.
Thanks. I guess a question or to start. So I know that oh, actually, Jamie. So just a message from Jamie. It's working on simulating drone swarms and training them with multi-agent reinforcement learning techniques. One piece of code that he's been working on also has a supervised learning process which tries to identify the leader of a drone swarm. So yeah, starting question for Christian and Pascal. So I know that Jordan and Abraham, they both have an allocation on Cetonics, but not Topaz. Any advice on how they might be able to make use of that over the internship period, given that the internship wraps up on the 10th of February?
My question is, why don't they have an allocation of Topaz to begin with, if they're part of the internship projects, right?
So I think it's in Jordan's case, it's an ongoing project. So I guess back, last year it would have been when they applied, supervisor applied. It didn't factor in Topaz, I guess, or the migration process.
Oh, I see. Well, definitely we can arrange in a way that it will be part of the internship group. This has to be confirmed with Maciej, but I think we can just add him to the internship group so that he can access Topaz.
And also on that note, I mean, it depends on what you guys are using, because of course there's lots of cores per node on Cetonics. So if you can achieve pretty high compute on a given node, not quite equivalent to a GPU, but it all depends on what type of parallelism and what you're using, right? So if you're using sort of quite vanilla frameworks, and of course they're really kind of meant to kind of do, they're really kind of optimized to make use of GPUs. But if you have something else, then of course you could just use all the cores on a compute node, and that's pretty fast. and that would allow you to do lots of compute.
So I know that, Abraham, you're starting off anyhow at this point, you're doing a parameter search. So in that context, it seems like Cetonics is going to be pretty useful because you can use the OpenMP threading and then parallelize across your parameters.
Yeah, exactly. That's precisely the point that I'm trying to optimize and using Cetonics, because the last simulation I did for validating my script, the process required more than almost 1 or 2 days for converging. So I would like to optimize that kind of time for computing all those solutions. But yeah, basically what I'm trying to do at the moment.
Right, okay.
So we have a question. Oh, sorry, Pascal.
I was gonna say, Abraham, do you have a way of multi-noding that as well, or no? In your parameter search, because certainly you could use, I mean, if it's just a parameter search, in principle, depending on what you're doing, how you're doing this, you just grab lots of nodes. And so
yeah, it's a multi-parameter training. For the XGBoost, it's very complex to train the model. It requires like 12 different parameters. And in this case, I'm using, I was going to use the random search approach. However, I found out the way to utilize Bayesian optimization, which was much better and actually a little bit faster.
Okay, but you know if, I mean, yeah, technically you can access from computer nodes, but of course best to do the data locally. You could, as I said, go multi-node as a way of reducing the time scale, the time it takes to do get convergence, if you're looking at something like that. So there's routes around having Cetonics. This is true for everybody. I'm using Cetonics without the GPUs because yes, GPU provides concentration of compute, but if you have a way of distributing your compute, then it'll be fine. It's just you have to have something in place to do that. So if you have Dask orchestration in some Pythonic workflow, which is maybe some way some people are doing that, then certainly that's not a big deal. But it all depends on what software you're actually using to do the task you want to do.
Okay, well, in this case, they didn't use Python, but the libraries for the task is a library called HyperOpt, and I think the much more complicated library for implementing Cetonics is Rate Soon. It's very difficult to use it. It took me a while to install such library in my computer.
I don't think you can use HyperOpt as a multi-node stuff. You'd have to write the orchestration yourself, I think.
All right.
So a question from Helen. Is there a standard way to use BigQuery on Topaz, or should we download the data locally first and move it across?
I mean, I would think I would always download the data locally. This is just much faster. I'm not familiar with BigQuery, but I mean, no matter what, local data is always better. So unless you're waiting for ages and ages and ages, but otherwise locality is always better. So if possible, I would definitely make data local, especially if you're going to transfer it to a GPU.
So sorry, Helen?
Oh, sorry. I was just wondering because I think I've got to actually get a different application to use to download that. So yeah, I was just wondering if there was something already set up in Topaz, but that's okay. If there's not, I'll just do it the way that other people have done it.
I mean, as far as I know, I mean, someone might have done it, but I don't think anybody. It's definitely not a system-wide thing in terms of BigQuery for Topaz.
So I think so when you say locally, you're referring to whether or not you're downloading it from like a remote server onto Topaz, or are you talking about working off Topaz somewhere and transferring it?
Yeah. Just onto my local machine.
I would transfer it to Scratch on Topaz for any sort of compute that you're going to do on Topaz, just to minimize congestion and other impacts that you have just transferring data.
So a question from Jamie. Only just started migrating some code from my computer to Topaz. How would you recommend going about working out what to set the various SBatch parameters to?
I think this is a good case of promoting our documentation. We have lots of examples in our online documentation on how to use the scheduler, so Slarm, and especially we have examples of batch scripts with the various parameters. So it's a good 1 hour well spent reading through the documentation, and it also depends on what you need to do, right? For GPU computing, I guess one important thing to remember is to ask for GPUs. Otherwise, you won't get GPUs. Your program won't see GPUs unless you explicitly ask for them. Even though you are given a GPU node, you won't be given GPUs. And then you have to set the basic options are the time you want your program to execute for, the maximum time limit. The partition on Topaz must be, I guess, the GPU queue, and the number of tasks you want to execute on the machine. But this is better explained also in our documentation. You'll find some examples, and I'm pretty sure those will answer your question.
Yeah, the only other advice I would give on top of that is choose small initially. So like 1 GPU, a little bit of time, the debug queue. So there's GPU queue -dev to start off testing what you've got to see if you're happy with what's going on. And also give you a guidance of, how long stuff might actually take and how much resources it might actually consume.
Thanks.
I guess we had another question from David that we kind of skipped.
It might be, yes. So it might actually be good as well. So there's a question. How do you recommend allocating nodes for the distributed scheduler in the case of Dask? So before answering that, it might be nice to get just a quick summary of what Dask is and why you'd be using it. Christian or Pascal, just for the rest of the group.
What's your course?
Yeah.
What's your course?
So I guess they can let us know how it's using Dask and in which. The answer to this question is there is no particular way of allocating nodes or tasks with Slarm. It's like any other job. You ask for many nodes, and then the scheduler decides which nodes to give to you. For Topaz in particular, I don't think there is any preference. Just ask for a bunch of nodes, and then Dask will handle itself the communication for its particular distributed computational model. But as far as our scheduler Slarm is concerned, it allocates nodes the same way for us other jobs.
Yeah, the other stuff as well is, of course, you can get Dask to essentially submit an SBatch script on your behalf, kind of do the orchestration that way. but I mean, essentially the same thing. There's no particular, I mean, there's the semantics of actually setting up and telling, let's say you want DAS to submit on your behalf, right? Then making sure you've got the right syntax and the right clusters and everything else. And there's online tutorials on Dask and running Dask on Slurm. We don't have any on our documentation because it's not something we particularly sort of promote, but there's certainly documentation to how to incorporate, how to get Dask to talk to Slurm. And if you're just having Slurm run, and then you're running something that has internally got Dask orchestration within that envelope of resources, then it's just a matter of coding up the Python so that you have the Dask orchestration the way you want it to within some resource envelope. But my suggestion, which is if you're going to go really multi-node stuff, would be to have Dask, talk to ShedMD so you can visualize what Dask is doing as it's kind of deploying stuff in the containers, because it will obviously spawn stuff and you can actually visualize what's going on as certain tasks are finishing. I'll try to find a nice documentation, but I mean, if you just search for Dask Slurm examples, then you'll find on the one the Dask sort of README docs and job queue. So it's the Dask job queue. They've got some example deployments. I do not think I have one for Topaz lying around, but it's not that difficult to write them from scratch.
So just a question that Pascal, that what is Dask? Because I don't think most of the folks here would have come across it yet.
So Dask is, I mean, essentially it's meant to fill the void of parallel computing in Python. So you have MPI for Pi, but Dask has got another take on it to do essentially orchestration of Pythonic tasks. And it's not dependent necessarily on MPI, but it allows essentially a flexible library of parallel computing. Essentially you spawn off Pythonic tasks and Dask does the orchestration. If you have something that is then also MPI, you would have essentially Dask plus MPI for Pi. So Dask would say, this thing is going to be launched as a Pythonic task in this sort of envelope of resources. You would run MPI for Pi internally so that you could have internal communication. But you can also have Dask finish a Python task and take the outputs of the Python task and provide it to other Pythonic tasks that then have to launch afterwards. So if you have, it's essentially a way of doing task-based parallelism because it's a very flexible library for parallel computing. If you just go to the Dask org, I can try to find something that's also a bit more, let's say, example rich. There's some tutorials that are a bit more example rich of what, rather than what the Dask documentation is, that kind of does a better description of exactly what it's doing, but it's essentially task-based parallelism for Python.
I suppose to be more specific on that question, the biggest bottleneck for me when launching significantly large tasks is that the scheduler can only process so many tasks per second. And I find that there is, in all the systems I've been using, that there's discrepancies between the single core performance of nodes that I'm working on. And it's that, is it a bad idea to just try and ask for well, I suppose you can't ask for specific good performing nodes to chuck the scheduler on. And the answer, is there a way around that?
No, because if you think about this, right, there's just context switching happening. So if you're launching lots and lots of small tasks that take a few seconds, then one, there's a lot of overhead even for Dask to do stuff. And then there's also context switching because you have the OS system stuff happening on various cores. And so, especially if tasks are very, very short, then I imagine you'll get load imbalances. Like some things that you would expect to all complete at the same time might have large discrepancies. There's some latency as well, especially if you're having Dask orchestrate, I don't know, 100,000 things. That's pushing it as well because it has to manage this orchestration. So there's a lot of overhead at that point. My suggestion at that point is to try to make a task actually much longer, to make it far more compute heavy. And have it extend for a longer period of time and try to do more per Dask task than have Dask try to orchestrate large numbers of very small tasks. That would be my best advice.
Yeah, it seems reasonable. And I suppose there's one follow-up is, well, no, I'll save it for later, but it's just Dask can be relatively fault tolerant, except in the case of file system interrupt, on file system issues, but I'll ask that later.
Well, yeah, I can just tell you, as far as I know, there's no way around that. Yeah, but there could be. I just don't know of one.
Thanks, David. Question I have is, so most people, when they come onto Topaz, they're bringing across code that they've written on their local machine, and it'll be running on a single GPU. Any advice as to how someone could go about judging whether or not they should move to using multiple GPUs, and how to go about identifying and sort of an effective and relatively pain-free way of doing so?
Pain-free, Edric, pain-free. That's
relatively pain-free.
I mean, I don't know if Christian has a better take, but I would say the second you can't stick everything on the GPU in one go would be multiple GPUs rather than taking portions and patches, if possible.
So it really depends on why you want to go to multi-GPUs. Is because you don't have enough memory, or because you can process more? So if you don't have enough memory, that's pretty straightforward. You won't fit on a single GPU, the job will fail, I guess. Or if you think you can process more, the way of doing that is essentially, well, what I would look for is first is seeing if the GPU is being utilized like close to 100% of the time. So if you monitor the GPU usage through the NVIDIA Semi tool and you see it's always 100% and your job is taking a few minutes to run, then I wonder, if adding more GPUs could actually help. But if you see that your GPU is probably not running 100% of the time, but it's idle 40% of the time, for instance, then there might be space for optimizing the way you submit work to the GPU. So packing more work to the GPU, and essentially always at the end, it's a good indication is plotting the total work time as you add more GPUs. And if you at some point you plateau, you cannot finish quicker, then you reach the maximum number of GPUs that can give you some benefit. Adding more won't give you more benefits, right? So that's a very quick way of testing it. Add GPUs until you don't get improvements for what you're asking for.
So when you say if your job doesn't fit in the GPU memory, is that if your say your batch size is very, very small, proportionate to your actual, say, data set, would that be is that the sort of scenario you're thinking about? So I can only fit like a small amount of my training data set at any one point of time into VRAM?
Yes.
Yeah.
I think of that.
I mean, the other thing would be also is if literally in the example of the large images, right? If an image is so large that you can't fit a single one onto a GPU, or you can fit a single one but not anything else, then it'd be like, well, okay, then multi-GPU, because then at least you could have the GPU process stuff and chat to each other. The MPI, the GPU to GPU MPI performance isn't amazing on Topaz, right? But it is certainly better if you are doing communication between GPUs to still try to communicate between GPUs rather than, let's say, GPU, host to GPU, GPU back to host to another host, host to GPU, because that's a decent amount of transfer. So if people are using MPI, then a GPU to GPU communication is certainly something to look into if they haven't done it yet. for multi.
We actually have also the P100 nodes, right? They're still there.
Yeah.
So those have the NVLink between GPUs. So multi-GPU on those P100s should be working fine. But that's not the GPU queue partition. It's the NVLink partition. So if you're doing multi-GPU stuff, then try run your jobs there first.
So with NVLink, can they expect their TensorFlow or PyTorch to identify that there's multiple devices, multiple GPUs available, and just start using them without any changes to their project settings?
Yeah, it's transparent. So the same code we run on the NVLink, but much faster.
Yeah, so the main thing is, right, if you ask within SBatch a resource request, at least for TensorFlow and a couple other packages, you're given that resource envelope, it will automatically start picking up what's available to it, and then do its, because they've already set it up to try to do this orchestration. So if you run on GPU, the queue, or the NVLink queue, it will do GPU to GPU communication when necessary. You don't have to worry about it. You would just notice that it's much faster on the NVLink setup. If you were sampling the transfer speeds, they would be faster.
So it's transparent in both. If you are working on a project where you've noticed that the VRAM is a limitation, trying out NVLink queue would probably be a good sort of first step to getting a bit more performance.
Yeah, it's not a bad thing. The main thing would be is if you knew that there's a lot of GPU to GPU communication, that's when I'd definitely go to NVLink. Otherwise, if there's not much, then probably stick to the GPU queue.
Also, because when you work on the NVLink partition, you ask for the entire node and all the GPUs, so you will be charged much more than when running on the GPU queue partition. So use the NVLink if you are sure that you're going to actually benefit from it.
So to definitely run a couple tests before submitting a 24-hour job.
Always. Yeah.
Earlier mentioned using NVIDIA SMI to take a look at GPU utilization. There any documentation on using that utility on Topaz?
I don't think we have a documentation on it. We just log into the compute nodes you're running on and run NVIDIA SMI on that node. You should be able to see the activity on the GPUs.
I think you have to do it with srun for it to actually see the GPUs, right?
So actually, this is an interesting question. If you log in, this is my experience, if you log in with SSH without SBatch or SLOC, then you're outside the SLARM scheduler and you can actually see all the devices.
Okay. Because I think another gotcha in this case is if you're running something like Jupyter Notebook or a VS Code or something, and you bring up an interactive shell, that interactive shell may not actually be able to see the GPUs, and so NVIDIA SMI will fail in that. You'll actually have to have a shell that's GPU enabled.
Yes. So if you are inside an SLOC, an interactive allocation, or even within a batch script, you should use srun to see GPUs. Because in that case, the resources are managed by SLARM. But if you just SSH into the node, then you can see the GPUs normally.
Yep. So how would they determine, how could someone determine which node they should be SSHing into if they wanted to look at the performance? Say you've used SBatch to submit a job. How would they, what's your next step?
So you can look at your currently running jobs using SQ. And I think either both SQ and S account as at commands, they have options to print out which nodes you are running on. So you can print the list of nodes you're using, and then you can use those names to SSH into them from the login nodes. So you connect to the login nodes, then you SSH to the compute node, specifying just the name. No need to the entire Pawsey.org.au.
Thanks. So NVIDIA SMI is a really useful utility. Just to emphasize that. It shows you percentage of GPU utilization, shows you the amount of memory you're using, particular tasks that are currently running on the GPU. So it's when I'm testing out GPU of code that I'm writing, I usually have a second window open that utility running just as a first sort of port of call to take a look at performance and know that I'm actually executing on the GPU device as well.
There's also a nice Python utility called NVI top, which gives you similar stats and is more interactive if you're that interested and have a Python environment set up.
Cool, thanks for the suggestion.
Well, we've just hit the top of the hour. So just maybe one last moment for any more questions from the interns. Not, we'll wrap up.
I guess always remember we can write an email to the help desk and we try to reply to your questions.
I suppose just to finish off, Christian, is there anything that you wish new users were aware of, or any gotchas or sections in the documentation you would, in a perfect world, you would like everyone to go over and be familiar with? Maybe just to pull everyone's focus right towards where they could learn more.
I think just go spend a day just going through the entire documentation. If you can, you will learn lots of stuff on how to use the supercomputer itself. Also for your future, in the future when you need to use other resources or run other type of workloads, it's very useful to know those things actually work, and will save you a lot of time later. So a day well spent on the documentation is a good thing. It helps a lot.
Nicely put.
So that's a Christmas reading, the Pawsey documentation.
Sitting there with a bit of eggnog on your laptop,
yeah,
for the fire, yeah, or by the esky. Great. Well, thanks so much, Christian and Pascal, for joining us for the session. Hope it's been helpful. And yeah, as Christian said, you can always get in touch with the help desk or reach out to myself, David, or Emily if you want to pursue any ideas that come out of this session. So, thanks so much for joining us.
Thank you. See ya.
Thank you. All right, actually, can I just ask one quick question?
Sure thing.